Hello everyone, and thanks for coming to our talk. My name is Andrea Frittoli.
I'm Kyra Wulffert.
And thank you for the introduction. So we'll be talking today about how we apply machine learning to continuous integration. Just briefly, I wanted to talk about the team. Matthew is not here today, but Matthew and myself, we used to maintain the continuous integration system for a rather large open source project, and along with other folks. And we had kind of a daily issue of a large amount of issues to deal with. And we thought, well, this is maybe a type of problem where machine learning could help us. So we kind of lacked the machine learning expertise at the time. So we talked to Kyra and we said, oh, look, we have this open data set. It's rather large. It looks like an interesting problem. Can you help us? And Kyra decided to join the project. So the team was formed. And we had our machine learning expert on the team. So I wanted to start talking about where do we get the data from. But first, I just wanted to ask how many of you are familiar with the concept of continuous integration? Okay, that's quite a few. That's good. So as I was saying, we were working for this large open source project. So the graph here shows, gives an idea of the test that we were running as part of continuous integration. So the scale here is in the order of 10 of millions. So we had quite a large amount of, not only quite a large open source project, but quite a large amount of contribution to the project. Every contribution which is done to the project is tested, goes through the CI system, continuous integration system, which means that we were generating a lot of data. For continuous integration system, it's very important to be stable, to give a good experience to the developers that are contributing to the project, because otherwise they will not be motivated to contribute anymore. And at this scale, you start running into problems, because when you run a test many times, it's quite likely that you will run into race conditions, for instance, if there is any race condition, either in the test or the software that you're testing. So there is a good deal amount of triaging of failures that is required. And these failures may not be related to an issue with the code that was submitted to the software, but actually maybe to the testing infrastructure itself, like temporary infrastructure failures or race condition in the software. So here we thought, okay, maybe machine learning can help us. Specifically, the project we were working on is OpenStack. OpenStack is a cloud management platform, which means that to test it, to run integration tests for OpenStack, what we did is every time we wanted to run the test, we had to stand up a whole cloud. So we did them into virtual machines. So for every test, we have a virtual machine where OpenStack is set up, all the services are up and running there. And then we exercise the cloud API using different integration tests. And this generates a lot of CPU, memory, and disk usage, and network I/O on the VM. So as part of the CI system, we collect all the logs from the application, but we also collect all the information about what the system is doing, so what type of CPU usage we have. We use a tool called dstat that allows us to collect with a certain frequency, which is 1 second, all this data into files, and then these files are stored after the test is completed. This is done because after the test is completed, the virtual machine is deleted. So if someone needs to go and look in what happened to the system, all the logs needs to be uploaded into an external system. So the graph here shows an example of normalized data that is taken from the dstat data from CI job runs. I also wanted to mention that in OpenStack, this continuous integration system is set up in a way that there is an initial testing that is done when some code is proposed to the system, which we call check testing. And once the code has been reviewed by humans and it has been tested initially, then it goes through gate testing. So we decided to use only the data from the gate testing and not from the check testing because of the noise. In the check testing, there is much more noise, in the system because it could be that the code is broken. Maybe it's not even passing unit tests, while we want to have to look into failures that are not related to that, but related maybe to infrastructure issues or race condition, as I mentioned earlier. So something that we realized pretty soon, sorry, is because there is a lot of data being generated, and it's an open source project, and we have limited amount of resources which are donated by people that contributes to the OpenStack Foundation, but that means that we cannot keep on the OpenStack side the data from the CI system indefinitely, so it has to be deleted and cleaned up on a regular basis. But because we wanted to apply machine learning to it, we needed to have a good size data set. So we realized, okay, maybe we should start collecting this data, storing it separately from what OpenStack does. So we set up a small automation system that pulls every time a CI job is completed. It pulls the log from the CI system. It applies initial lightweight validation just to make sure we are not storing data that we are not going to need later on. And then it stores the data into an object storage in the cloud. We used OpenWhisk's serverless platform for this. So once we had the data, we started working on the data preparation part. We built a small piece of open source software that we call it CML. It stands for CI for machine learning. And this is basically a wrapper written in Python that allows us to do different things that we need in our workflow. So the initial thing that we want to do is create the data sets and later experiments and training. So this is an example on the top corner there of how you might create a data set. The things that we do when we create a data set, we define the size of the data set starting from the original raw data. We apply some filtering, we normalize the data, and we store the result into a named data set, again, in a bucket on the cloud, so in an object storage in the cloud. This way, we have a reusable unit that we call the data set that we can then use to run multiple experiments on. This is also I wanted to mention, this is done in a way that can be easily containerized, which means that we can run this kind of dataset creation either on your laptop, but we can easily run it in the cloud. So for instance, we used a tool like Tekton, which allows you to run tasks and pipelines on top of Kubernetes. And so we use Tekton tasks to create our datasets. Okay, about the data. So here you're presenting what the distant data looks like. It's actually much larger. It's just a small subset, but just to give you an idea. So in every row, every second, there is a sample of the data that is collected from the system. USR means the CPU utilization in user space. Use refers to the memory. Read is for disk I/O, and 1M means the system average load over 1 minute. There are many more features that this starts collecting. But so we did two types of selections. So the vertical selections means that we select certain features only out of the whole data set that we had, because we consider those as more relevant. So looking at the data, we saw that certain features were not really carrying much information, or they were carrying the same information in different columns. The other type of selection that we did was on the rows horizontal. So we downsampled the data to reduce the amount of data to improve our computational speed, so to say. And we did that using then applying average over the interval that we use for downsampling. One thing that we learned here was that data is not always clean as perfect as we might expect. So some samples were missing, and we were hitting, for instance, NAN, not a number, and other type of issues. So you always have to include some cleanup steps in your normalization procedure. Going back. So if you look at the crossing of the columns and the gray columns and lines there, you see that there are 6 numbers in this example. So this is the data that is generated by one CI job. And we unrolled it in a way that the 6 numbers become one line. So the 3 lines in the table on the left side are 3 different CI jobs with the data unrolled. And we labeled data so that, for instance, the CPU in the sample 1 is USR 1 and so forth. After that, we did applied simple normalization just to make sure that all the values are between -1 and +1, just again to reduce the computational effort. And finally, from our initial data set and normalized data set, we split it in 3 parts, one for training, one for dev, and one for test. Even though, in fact, we realized that we didn't really need dev, so we actually ended up using only training and test to give more data into the training side. We also wrote some functions, input function, that we use to feed the training data into the model, because we run the data over multiple epochs, and we want to make sure that the order is randomized every time, so the model doesn't go over the data again and again in the same order, which improves the training. Finally, we also wrote some more CMOL tools that allow us to define experiments and run training. So an experiment is just a collection of metadata that describes what type of estimator or what type of model we want to use for training, and the collection of the hyperparameters. This is, again, it's a small Python tool that can be easily containerized and run in the cloud. And for training, again, we wrote the CMOL tool that can be used also to run on your laptop, or can be used to run through different frameworks like Tekton or Fido. So we did things this way because we wanted to have like a common entry point, which is our CMOL wrapper for running trainings, and we wanted to maintain the ability of using different frameworks for the training. So we used the TensorFlow API a lot, but we also use Kyras, we used scikit-learn for different aspects of our work. And also we wanted to have the ability, in terms of testing infrastructure, as I said before, to run either on our laptop, but also to trigger trainings or dataset creation from our Jupyter notebook, or ultimately, when everything was set up and ready, to trigger our experiment in the cloud so we could run multiple experiments in parallel. We also wrote an Helm chart to deploy our CMOL application to set up this kind of prediction pipeline. This works the way that every time an OpenStack CI job is completed, then an event is triggered using a protocol called MQTT, which goes through a system called Firehose. And then our CMOL application has two components, the prediction part and the training part. The prediction receives a notification, it pulls out the data, reapplies the normalization on the fly, and emits a prediction. And same for the training. So one is consuming the data to generate the prediction, and the training is doing training on the new data. We can do what we call continuous training because we trust the CI system as a trusted source of data for doing continuous training. The prediction that is produced by the prediction component can be used then to give immediate feedback, for instance, from the developer. So if we extract some insight from the data, we could publish back to GitHub or Gerrit saying the data that we obtained from the prediction.
So with the workflow and the infrastructure in place, then we plan to run a set of experiments to see how much information we could obtain using machine learning on the distant data we had available. So the first set of experiments we ran was supervised learning, doing binary classification. So first we wanted to evaluate if a trained model could accurately classify a CI job as pass or fail. For this we used a classic deep neural network, and our data set was based on one specific CI job called Tempestful, which is one of the most common CI jobs for OpenStack integration. And these data, as Andrea was explaining, was coming from the gate pipeline only, which is less noisy. So we use as hyperparameters a ReLU activation function, a sigmoid output layer, which is quite useful for these classification problems. We went for the AdaGrad optimizer, which is self-adapting, and started with a learning rate of 0.05. And as we can see in the figure, we used the network topology with 5 hidden layers and 100 cells. Our primary metric was accuracy. We also kept an eye on the loss. And the first evaluation we wanted to do was to see if there was one specific feature or a set of features that will achieve a high accuracy. So in our initial data set, we were contemplating as features the user CPU, the use memory, and the system load, 1M here in our figures. And we started with a data resolution of 1 minute. On the top figure, we are displaying 1 minus accuracy because it was better for visibility. And there we can see that the best combination of features was user CPU and system load. And then we wanted to see if it was even it was better to even improve more this accuracy achieved. And then we ran the experiments using different data resolution ranging from 10 seconds to 10 minutes, and found that the 10 seconds data resolution had a slightly better accuracy. As it was not a much better value as for the 1 minute data resolution, we dig deeper into the matrix to see if there was something special or different between them, and saw that precision recall and F1 score, which is the weight average of precision and recall, were very similar. So from this, we could say that in order to have less computational effort, less computational cost, we could just keep using the model with 1 minute resolution and still get good results. The next point we wanted to evaluate was if this trained model was portable to similar CI jobs. So we took the trained model with the best combination of features we found and the 1 minute resolution as data sampling, and evaluated it with a similar CI job called TempestFull PI3, which was using Python 3 and 1 component less in comparison to the TempestFull. And we found that the metrics were pretty good, not as good as for the TempestFull, but it was we could consider it as positive, and that the model could be portable to similar CI jobs. So this one was one of the main conclusions from our first set of experiments. And then the next important point from these experiments is that besides providing us the information whether the test was pass or fail, which anyways we had it, with this model we could see like the prediction confidence, and this might be useful for the people maintaining the CI system in order to see if there is a certain degradation, because if the prediction is correct but the confidence is getting lower, then that could mean that something in the system is failing or needs attention. So this could be used for an early warning system for the operators of the system. The second set of experiments we ran was supervised learning on multiple classification, where our classes were the hosting cloud providers. These are the cloud operators providing the virtual machines to run the CI jobs. In our initial data set, we had 10 classes, or 10 cloud providers, and we just used the same CI job for our data set, and exactly the same network and model we had for the binary classification after our first set of experiments, and ran it, and found that the results were not good at all. So we ran again the same methodology we did for the binary classification test, and first tried different combination of features and different data resolutions. I found that the results were not getting better. Then we tried different network topologies, so a more complex and a less complex network topology, but still the improvement was not significant. And then at this point, it was clear that the datasets, in the datasets, the classes were not distinguishable enough for the ML model to differentiate between them. So we went back to the data and analyzed it and found that some cloud providers had several regions. So we decided to group those classes and consider them a single class. In this way, so we had a new number of classes of 6 from 10, which was the initial number. And run again the same set of experiments with different feature sets and with different resolutions, and got a very good accuracy. So this was the trick making us move forward in the training of our model. We wanted to evaluate if it was possible to improve this number, and then try again with different network topologies, and found that by decreasing the complexity of the network from 5 hidden layers to 3, the accuracy was getting better. Then, as we did for the binary classification, we dig deeper into the matrix. When we ran this experiment to find the matrix, the data set was containing a new cloud provider, and found that for those cloud providers with most samples in the data set, the metrics were pretty high and also good. But for those with less data, it's not surprising, but with those with less data, then the metrics were not good at all. So this gave us the inspiration to run a new experiment where we wanted to see if it was possible for the model without supervised learning, so with unsupervised learning, to cluster and group all those cloud providers that had the highest amount of data in the data set. So we ran with the same combination of features and the data set resolution of 1 minute. We ran a clustering algorithm, k-means. For deciding the number of clusters, we just ran the elbow method and checked the silhouette score, and the recommendation was between 3 and 4, which was in line with our expectation because that was the number of cloud providers with the highest amount of data in the data set. And then we ran both experiments with 3 clusters and 4 clusters. In the experiment with 3 clusters, unfortunately, 1 cluster was getting 2 of the 3 cloud providers with the highest support. So it wasn't really significant. But for the experiment with 4 clusters, these 3 cloud providers were clustered in different clusters separately. And for both experiments, we could see that 1 cluster had 1 cloud provider with very little noise. So this was a very interesting insight from the experiment. So from this set of multi-class experiments, we saw that reducing the complexity of the network, we got better accuracy. We could reuse the results from the binary classification sets regarding combination of features and data resolution. We found that this model, if applied to the Tempest full with Python 3, was not portable. But we found that unsupervised learning and clustering could be found to get some insights from the distant data. And that's an area we want to keep working on. Mm-hmm. So in general, we could prove that just using the system data, in this case, we were using the distant generated data, you can get information from the CI jobs, you can get some early warning flags that will be useful for the people maintaining the system. We saw also that this data can be, has potential to run unsupervised learning and get maybe some clustering of failures. In general, from the project, we found that it was really important to start collecting data since the beginning and creating a pipeline to process it and normalize it, especially if it is open data, even better. In our team, we had different knowledge domains, so it was very helpful to know better our data and to run the initial filtering and cleaning up, and also then when we were in the multi-class experiments to think about why we are not moving forward and what can we do to get better. So that was the idea, to reduce the classes, which proved to be good. And our explanation for that was that cloud providers might use the same hardware layout for the different regions. So that's why reducing the classes in that way made sense. This might be evident, but we recommend highly to work with cloud tools because these allow collaboration. So we are all located in different parts of the world with different time zones. And also it made possible to train full scale. We were using, as Andrea said, different ML tools, and just use whatever you feel that is helpful for your purposes. So we are still working on this project, and one of the things we want to evaluate is why this specific cloud provider could be clustered so uniquely. So there is something about it that is quite representative, and we want to run some interpretability on this information to find out why the clustering worked like that. There were great talks these days about interpretability. We want also to extend the data set to include some information from the system application logs in order to continue exploring the clustering part of the CI jobs and do, for instance, a clustering of failed CI jobs. And as next work, we want to also keep working on the portability of the CI job, for instance, for multi-class problems. So all our work is available on these links in GitHub, and it's open for the community. Also, if you want to collaborate, even better. So we still have some time, so if you want to take any questions, so we can do it now, or if you want to contact us, so these are our contact information, and you can always let us know. And yeah, thank you very much for being here at the very last talk of the conference.